know what latitude and longitude are for, positioning ourselves globally. But did you also know the method for creating the lines gives us our distance and speed measurements? So how do they work? If the world were flat, this would be easy, right? If Earth really were flat, we could just put a grid over the map and label the two axes. Perhaps letters for the y-axis and numbers for the x-axis. Then, as we moved around the world, we would just use the y and x to understand our position. This isn't too dissimilar to how latitude and longitude are used in practice, but knowing how the lines are created is important. Contrary to flat earthers' belief, if we continue to sail west, we won't actually fall off the world's edge. But of course, when we sail west, we move from the left of the chart to the right. That's because, on this chart, lines 1 and 19 are essentially the same place. Similarly, if we think about how we've unwrapped the globe to create our flat chart, all vertical lines run from one Earth spot to another. If we travelled northward up any of these lines, we end up at the same place, the North Pole. So the whole of line M is the North Pole and line A is the South Pole. So let's take a look at how these lines are created. The theory behind latitude and longitude can be traced back to this guy in the 3rd century BC. By the 2nd century BC, this chap, Hipparchus, started using maths to specify places on Earth uniquely. Essentially, we need a way to reference ourselves up, down, left or right on the chart, and this is all done from one single spot on the globe. But why here, and how are these lines created? We'll start by looking at the horizontal lines across the chart. We use these to establish how far up or down the globe we are. These are lines, or parallels, of latitude. We need to go to Earth's centre to understand how they're created. Once there, we can see we have to rotate 180 degrees to change from pointing down to up. If we were to protrude lines from the centre of Earth to the surface of 90 degrees, we could create a line around the globe at its fattest point. But of course, we all know this line, it's the equator. It has effectively split the globe into the northern and southern hemispheres. This is important in terms of understanding how latitude works. The equator becomes our start point. We are either somewhere north of the equator or south of the equator. In latitude terms, the equator is 0 degrees. Returning to Earth's centre is the easiest way to see how this works. Now we have a start point, the equator, we can create lines that run parallel with it, hence their name, parallels of latitude. Then, each can be referenced using its angle back to Earth's centre. This can be done to a maximum of 90 degrees north, straight up, or 90 degrees south, straight down. So let's unroll Earth and see how that looks on a flat chart. In this view, we can see how we can reference ourselves anywhere in degrees, north or south of the equator. Now we've seen how lines of latitude are created, let's look at the lines of longitude, the ones running vertically across the chart. If we were to walk around the equator, we would complete a circle, 360 degrees. This is known as a great circle, the furthest you can travel in the same direction around the globe. We can create other great circles too by travelling north through the North Pole, then heading south through the South Pole and back to the equator again. The maximum distance we could travel around Earth in one direction. Let's look at these north-south great circles. If we started one at each degree around the equator, passing through the North Pole and South Pole and back again, we create our lines of longitude. Each one is known as a meridian, dissecting Earth into equal slices. Each of these meridians splits the globe in two, creating a left and right half, or west and east hemisphere. So we could be east or west of any of these meridians, and that right there is the problem. We need a start point. Where is zero? For a long time, different nations used different lines as their start point, each producing charts that were from their definition of where east met west. That's where these guys come in. In 1884, the catchily titled International Meridian Conference in Washington, they came together and voted on a standard for the world to adopt. The chosen meridian? Greenwich, the zero marker, where east meets west, the prime meridian. Let's flatten this out and look at the prime meridian on our chart. As we move west from 0 degrees, our longitude increases in a westerly direction until we reach 180 degrees, the opposite side of the globe. 180 degrees is the marker that puts us in the eastern hemisphere, and our degrees will slowly reduce until we return to the prime meridian. Let's put the whole thing together on our chart. We can ditch our battleship layout and replace it with our newly learned north-south, east-west axis. We have a starting point for our positions. The cross in the middle is neither north nor south, west nor east, 0 degrees. Everything builds out from here. We've split the globe into 4 quarters: northeast, southeast, southwest and northwest. Now we can reference ourselves in any of these quarters using the appropriate degrees. For example, this position would be 30 degrees south, 80 degrees west. Great, so we have a grid for the globe in degrees. Let's take a look at the scale on a chart. If we zoom in, we can see the 50 degree north latitude labelled. We know it's north because the numbers increase as we move north on the chart. If we're in the southern hemisphere, south of the equator, the degrees would decrease as we move north and increase as we move south. As we move up the chart, we get to the next incremental degree of latitude, in this case 51 degrees. Of course, each degree covers quite a large area, so we need a way to divide them up. To give you a sense of size, the 50 degree latitude is in France, while the 51 degree latitude is in England. Crossing the English Channel at its narrowest point between Dover and Calais covers about 1/3 of a degree of latitude. So we need a way to segment each degree. Each one is divided into minutes, 60 of them, annotated using a single quote. As we move north, the minutes increase until we reach the next degree. Remember, this system was devised when all numbers were worked in units of 12 or 60, with some logic in mind. 12 or 60 can be easily divided by 2, 3 or 4, halves, thirds and quarters without the need to use fractions. The same measurement principles apply to longitude, our west or east scale. This chart is on the prime meridian, 0 degrees. If we go right, we increase our east longitude. If we travel back west, we pass the prime meridian and start increasing our west longitude. So we're starting to get a good position using degrees and minutes, but we can be more accurate than that. This large-scale chart is in the Western Hemisphere. We know this because the scale numbers are increasing as we move west. Most charts nowadays break the minutes up using a decimal scale, each one broken into units measurable and dividable by 10. On this chart you can see there are 10 individual units between each minute. When looking at a large-scale chart, we often find they don't cover a whole degree. In other words, the entire chart is less than 60 minutes of the scale. The appropriate degree for the chart will be labelled where this is the case. But remember, this is not a whole degree line, just a reference, so you know what degree area you're working in. In this case, the mark is at 1 degree 36 minutes of longitude. Great! So we can precisely locate a position on the chart using latitude and longitude. I've marked a small dot which we can find the position of. First, we know we're in the northwestern hemisphere because the latitude scale increases as we move north and the longitude scale increases as we move west. Next, we need to find the reference for what degree we're in. 50 degrees for the latitude and 1 degree for the longitude. Happy we've established that, it's on to the minutes. When looking at the latitude scale, we need to look for the number just to the south of our position because we're in the northern hemisphere. In this case, 43 minutes. Likewise, with longitude, we need to consider which way the scale is going. In this example, the scale goes from right to left, i.e. west, so we should use the number just to the right of our position. So looking at this, it would be 37 minutes. So we've narrowed our position to a single square on the chart. Then in the last stage, we get really accurate by using the decimal scale between the 2 minutes. Remembering to read them from the smaller minute to the larger minute. So our latitude decimal is decimal 30 and our longitude decimal is decimal 50. So our latitude and longitude in full is 50 degrees 43 minutes decimal 30 north, 001 degree 37 minutes decimal 50 west.